Okay, so flexural strength or ultimate calculations in pre-stressed concrete is not terribly different than in reinforced concrete. So in reinforced concrete, we would have our Whitney stress block, and we've got nothing counts in tension. For the concrete parts, we've got a tension here, a compression here, and we got that compression component from our Whitney stress block, and we got our tension component from area of the steel times Fy. The reason we got that tension component at ultimate as As times Fy is that we had an elastic, perfectly plastic steel in the rebar. So if that was 60 KSI rebar, it hit 60 and flattened off in our assumption in our elastic perfectly plastic curve, and so at ultimate it would also still be at 60. The C part is the same as for reinforced concrete and pre-stressed concrete. For pre-stress, the difference comes in this T term. So we'll have the same thing. We still have a Whitney stress block. We still don't count the concrete and tension down here because now we're at ultimate, and now we're at a place where we do have cracking. So the uncracked stuff still doesn't count. Here we have a little bit different case for the tension piece. So we have area of pre-stress, which makes sense. And then we have to have the stress and the steel at ultimate, and I'm going to call that stress pre-stress, because now our rebar curve or our steel curve starts to look more like this. There's not a well-defined yield point, and so we kind of need to know where we are on this curve. It's not elastic perfectly plastic, which means that there's not a single number for FPS here. We're going to have to calculate it based on where we are on that curve. So we can try to do that and do an iterative process, but in the code they actually allow you as an alternate, and so this is out of the code, and you can see the section number here, 20.3.2.3.1. In this piece of the code, I'd encourage you to go look it up, but I've put it in here. It says, as an alternate to the more accurate calculation based on strain compatibility, which I'll show you later, but that'll get you to a little closer to those points. But it's an iterative process. As an alternate that, they let you use this equation in the code for F sub PS. And what this is, if you look at this equation, there's a FPU term, so that's the 270, but then we have to, 270 being the max, all right? So then we have to modify that so that that 270 KSI has some kind of modifier that takes it back a little bit depending on a number of factors. And so that shows us the different contributions there in the equation. So the highest you're going to get here is FPU at 270. You're not going to see that. You might see it pretty close though. If you read carefully in the commentary on this section, it talks to you a little bit about the terms, but it also talks about something specific here. This says you're allowed to use this for bonded pre-stressed reinforcement. Okay, so this is bonded tendon, so this is pre-tensioned or post-tensioned with the grout inside the cross section, all bonded together. And if all pre-stressed reinforcement is in the tension zone and F sub SE, so the effective stress, is greater than half of 270, which means it's acting like pre-stress. So if you only put half the stress in, it's not really developing the pre-stress in the same way that we assume when we use this equation. So for most cases of bonded, this is what you're going to use. If the pre-stress reinforcement is in the compression zone, you just don't use this equation. You don't use that steel in this way because it's in compression. It's not the same type of curve. And then it gives you some items about compression reinforcement. If compression reinforcement is included, you have to just make sure that the term that includes the compression reinforcement is at least 0.17, and it talks about this over in the commentary. I'm going to have you go ahead and read that commentary. As we go through this equation, and I'll touch on this on the board in class as well, we have a couple terms. You know what beta 1 is. Okay, that's related to concrete strength. Rho sub p. Rho is a term, the reinforcement ratio, and then sub p means we're looking at pre-stress. You know F prime C, you know D. D sub p is the D to the pre-stressing steel instead of the reinforcing steel. So this equation is in a general form that assumes you have both some reinforcing steel and then you have some pre-stressing tendons. And I'm just going to make that a bigger circle. So it's giving you a D to the pre-stressing tendons and a D to the reinforcement. If you're only counting the pre-stress, which is conservative for this, and if it's primarily pre-stressed, which is, we're using uncracked sections, so that's the case. There's going to be some bar in there to hold the stirrup in and thing like that, and maybe for some crack control in slabs and such. But for the most part, we're looking at the pre-stress. If we get rid of the non-pre-stress term, so rho is going to be reinforcing bar, rho prime is going to be compression reinforcing bar. If those two things are zero, this term goes away, and we're left with this part of the equation. Alright, so in here things are looking fairly reasonable. We got FPU, which is 270, we got rho sub P, and we've got gamma sub P. So gamma P is down here in this table, okay, and it says if you've got a ratio of yield, which is actually hard to define, you know, somewhere in here kind of where is the yield, but there's no perfect definition of yield for this. But if you did that ratio, this is what gamma sub P. Now, the nice thing here is if you look over to this table in the commentary, this is what we really use. If we're using bars, stress relief strand, or low lax. So low lax is what we've been primarily using. It says that ratio is 0.9. So the gamma sub P that we use in that equation is 0.28. If we're not going to do stress relief strand unless we're investigating an older structure. If we do bar, then depending on what kind of bar, and ours are likely deformed, this would be this gamma P, which I think is 0.55, but I wrote over the top of it. There we go. It's 0.55. So 0.28 is the one that invariably we're using in this class because we'll usually be using strand. So you'll put 0.28 into the equation up here. Alright, so this equation isn't quite as hairy once you get rid of the bar terms on it. As an alternate, you also can have a case where excuse me. As an alternate, you may have unbonded tendons. And so I've pulled that piece out of the code for you. And for unbonded tendons, and we'll talk about this in class, but an unbonded tendon is going to be a case where you have no grouting, or you have, there's some options in bridges that aren't necessary to know about right now, but this is going to essentially, for our class, be an ungrouted tendon. It asks you the ratio of length to height, and then goes through and gives you these equations for your F sub PS. So we'll talk about that a little more as I go through some of the unbonded tendon requirements, but for now we're focusing on the F sub PS equation to calculate our ultimate.